Well, good afternoon. This is Mathman, and we've been talking about integrations, and in this video we go ahead and solve a number more of integrations using substitutive techniques. So I hope this will be of benefit to you, and here we go. There we go. I must have accidentally hit an integral of this nature. Cosine of x over 1 plus sine of x dx. And we want to know what that integral is. Well, we try substituting. U equals 1 plus sine of x. And du dx equals cosine of x dx. Cosine of x. So du equals cosine of x dx. And now we can put that substitution into this. And we've got cosine x dx, which is du over u. And that is the natural log of u plus c, and the natural log of u is, and I should erase that, u is 1 plus sine of x plus c. And that's the answer. Pretty simple substitution, but it's not necessarily straightforward. You have to kind of experiment in a sense. These are integrals that I've worked with over the years, many years, and so I'm familiar with the approach on solving them. Plus, I have my notes, which help me. Okay, I did select a pen. Okay, we've got like 30 examples here, so let's keep moving. The next integral we're given is 1/2 the integral of 2 cosine of 2x dx, and we got 1 plus sine of 2x. Well, we can make a couple of substitutions here. First, let's make u equals 2x and du equals 2 dx. So we have 1/2 2x. So we have 2 dx up here in the numerator. So we have cosine of u du over 1 plus sine of u. And now we're back to that form in the previous problem. So let's say z equals 1 plus sine of u, and dz equals cosine z dz. And now we have dz in the numerator and z in the denominator, and that equals 1/2 natural log of z plus c, but that's equal to 1/2 the natural log of 1 plus sine u plus c. And now we do our last substitution. 1/2, I'm putting it back into x, ln 1 plus sine of 2x plus c. And that is our answer. Let's take a look. I just want to make sure that we got that. Yes, we got the correct answer. And you can see here we employed two substitutions. One for the argument of the trigonometric functions, and one for the integrand of the integral, to get it into this form that we know is integrable. And then we go back and we substitute the parts that we made substitutions for, and we come out with our final answer. So there we go with the that problem. There are many problems that you can solve that way. But again, I remember one professor I had mentioned that there are many, many more integrals that can't be solved than can be solved. So that's a bit of a disparaging thought. So here we go. We're given another example. 1/2 2 times cosine of x dx over 1 plus 2 sine x. So here we make a substitution. We'll just say u equals 1 plus 2 sine of x, and du equals 1 or 2 cos x dx. And so what do we have here? We put those back into our equation. We got 2 cosine of x dx, so that's du. And the denominator is u. Again, we have the natural log, 1/2 the natural log of u. And that is equal to 1/2 the natural log of 1 plus 2 sine x plus c. Yeah, we can't forget the c. These are indefinite integrals, so we can't forget the c, the constant. So we're moving along. We're getting a lot of integrals done here. These are all pretty much the variants of the same thing. And here we go. Let's try this one. This one looks pretty interesting. So we've got the integrand is secant squared x dx, and we have 1 plus the tangent of x. So let's try our substitution again. U equals 1 plus tangent x, and du equals. Now, this is where things get a little interesting. We know that the u dx of 1 plus tangent x is equal to 0 plus d dx of tangent x, and that happens to be secant squared x. We've done enough of those to show that. So du equals secant squared x dx. So we have, once again, we have that same form. We can substitute I du over u, and we're back to ln of u plus c equals ln one plus tangent x plus c. And that should be the answer. That is. I hear something scratching at the ceiling, and I don't know what it is. It could be squirrels. We live out in the woods, so it could be anything making its home up there. Last night we had to put our kitty down. She was in major distress, suffering from cancer, and we had to take her to the emergency hospital, and they said there was nothing more we could do for her. It was a sad occasion, and so I'm a little bit tired. We didn't get home until 2 o'clock, and to bed till 4 o'clock, so it was a late night. Okay, so let's take a look at some more examples. We have x plus 1 to the third dx. Again, this is a polynomial, so we can use a substitute. U equals x plus 1 du equals dx, and we can say this is u to the third du. And now we can use our rule, which would say u to the fourth over 4 plus c, and now we substitute for u, and we have x plus 1 to the fourth over 4 plus c, and that's our answer. We're starting out easy, and we're moving to increasingly complex examples. So, I don't have the most comfortable setup here. All right, let's take a look at the next example. We have this one. We've already looked at an example like this. X to the third plus 3x squared plus 3x plus 1 dx. Now, our best bet is really to do it sort of term by term, using a substitution wouldn't be advantageous to us. So basically, we could either recognize that each term is how it's going to integrate, or we can just do it term by term just to show. So we go x to the third dx plus 3 x squared dx plus 3 x squared. Whoops, sorry, that was not a square. We'll get rid of that. 3x dx plus dx. And so now we can apply our polynomial formula, which is x to the fourth over 4 plus 3x to the third over 3 plus 3x squared over 2 plus x plus c. And now we can consolidate it. X to the fourth, we can go 1/4 x to the fourth plus x to the third plus 3/2 x squared plus x plus c. And that's our answer. And just to check, yep, no problems there. Let's close that one out, get ourselves a new screen, blank screen. We're really blowing through these, aren't we? Now here we go, where we might be able to use the substitution. We got, oops, I didn't choose the right pen, which happens sometimes. Okay, so we're given the integral 2x plus 1 to the 7th dx. So we can use the substitution for the integrand. U equals 2x plus 1 du equals 2 dx. So dx equals du on 2. So here we make our substitution. We've got u to the 7th, and dx is du on 2. So we have 1/2 u to the 8th on 8 plus c. So that's equal to 1/16 u to the 8th plus c. And the final substitution, 2x plus 1 to the 8th plus our constant. And that is our solution. The only thing different here is that you have to pay attention to your differential and make sure that you have it expressed correctly in the the general theme that we've been following here with these integrals. All right, so here we have another one. Now we're given a different one. Let's see, trigonometric. So we got sine x cosine x dx. Let's do a substitution. U equals sine of x du then equals cosine x dx. And we have that. So we have u du. And that's all it is. It's an integral of that form. So we have 1/2 u squared plus c. Now we substitute. For u, we got 1/2 sine squared x plus c. And that is our solution. Now, don't get caught up with the idea that you can easily have your mind jump to a regular trigonometric integral, and that would be wrong. It would be instinctive, but it would be wrong. So you don't want to think that way. You got to be a little bit more wary. So when you see an integrand like this, think substitution. Okay, it's not a typical trigonometric integral. So we just have to be careful with stuff like that. Just want to make sure that we don't get mixed up or tricked. And that's something that math professors love to do, is to throw stuff at you that could be tricky. So here we go. We got an integral. We got 1/2 sine 2x dx. Well, here we do use a substitution, but for the argument of the sine. So we say u equals 2x and du equals 2 dx. So dx equals du on 2. And so here we go. We got 1/2 sine of u, and dx is du on 2. So we have 1/4 sine u du. But we know what the sine of u du is. Remember, when we took our sine, we went y equals cosine x, dy equals sine of x dx, and then we have y equals sine x dx, and that is cosine x equals minus sine x dx. Well, here we don't have the negative sign up here, so I hate this when my hand does this. It is a bit sensitive. Okay, so we end up with 1/4 negative sine cosine of u plus c, and that's equal to minus 1/4 cosine of 2x plus c. And that's not a very good 1/4. Let's erase that and make a better 4. There we go. And let's see how we have that. That should be the solution. And it looks like I made a mistake in my, not in this is correct, but in my notes I made a mistake. I had the right substitution and all, but I didn't have the correct integrand, because here dx is du over 2, and that gets multiplied by 1/2, so then you end up with 1/4. So this is the right answer. Going through my notes, I found a mistake. I'm going to have to make a notation of that somehow. Okay, let's take a look at another one. Like I said, we're going to be doing all different types of integrals from now on. It's going to be an integral blitz. All right, so let's see. What do we have? We looked at that. Oh, let's see. Okay, I got this one. I don't know why we wrote it this way, but let's take it this way. We've got cosine x sine x dx, and u we're going to say is cosine x, and du is equal to negative sine x dx. Well, we have sine x dx in the integrand, but we don't have the minus sign, so we put the minus sign here and then put the minus sign out here. And so we have -1 times u du. And now we use our formula. We got negative u squared over 2 plus c, forgetting our equal signs. And now we put our substitution back, and we have minus 1/2 cosine squared of x plus c. And that is our answer. So, how many have we done so far? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 integrals. So, most of them are variants of the same theme, but these were problems that were given to me or to our class by Dr. Pine, and they're very progressive. The way he went, he progressed from straightforward problems into many difficult problems. I also went to the Handbook of Physics. It's a great big book. I have an old version of it that I got as a gift back when I was in college. I think it's the 64th edition. But the Handbook of Physics and Chemistry contains all the constants and everything that you need to know as a physicist. It's a wonderful, wonderful reference book. It has everything you can conceive of in a scientific way, including in the beginning about 30 or 40 pages of integrals and derivatives at the very beginning. So it gives you the tools at the beginning of the book. And I went through those. Instead of just taking the answer, I derived as many as I could to obtain the answer. And some of them were pretty interesting. And we'll be doing those as we move along. So here, this is a pretty straightforward one. We don't need much here to... Oh, let's see. Now this one actually is part of a bigger problem that I did. So let's erase this. I kind of screwed up. All right. Let's rewrite this problem. I didn't see it properly. 1 plus sine x to the 7th cosine x dx. Now we use the substitution. We go u equals 1 plus sine x, and du equals cosine x dx, which is what we do have. So now this just becomes u to the 7th du. And now we integrate. We got u to the 8th, 1/8 plus c. And now we resubstitute. We got 1/8, 1 plus sine x to the 8th plus c. So these aren't so tremendously hard, but again, you might be tempted to try and do a trigonometric equivalency when this is really a polynomial type problem that just happens to use the sine and the cosine function as variables. All right, so here we go. We're trying a new one. So here we go. We got u to the -3 du. Well, in this case, we can use our old polynomial formula. So we got u to the -3 plus 1 over -3 plus 1 plus c equals u to the -2 over 2 minus sine. And we could put it this way, -1/2 1 over u squared plus c. We can write it like this, minus 1/2 u to the minus 2 plus c. Well, we did already up here. So, don't need to do that again. That wasn't too bad a problem. Now here we go. Here's one that is kind of interesting. Let's write it down. We've got 1 over b a plus bx to the 1/2 dx. So here let's try a couple of, we'll try a substitution. So we go u equals a plus bx, du equals b dx, and dx then, dx equals du over b. So we have 1 over b, and we have, we do have dx, so we erase that because we have, whoops, I'm going to get my pen. We have dx and 1 over b, so we have u to the 1/2 du. Or wait a minute, just a second. I'm kind of screwing things up. Let's slow down a second. Okay, so we have our u. Our u is a plus bx, so we have u to the 1/2, and dx is du over b, so we have 1 over b, and dx is du over b. So here we got 1 over b squared, u to the 1/2 du. Now we employ our formula. We got 1 over b squared, u to the 3/2 over 3/2 plus c, and the final is 2 over 3b squared u to the 3/2 plus c. Now we make our substitution. 2/3 b squared and a plus bx to the 3/2 plus c. Okay, that was slightly different from what we had. And again, I wasn't careful in my notes. That's what threw me a little bit. This is the correct answer because what we have to substitute in there, all we have is dx. And dx is du over b. And we have 1 over b out here, so it's 1 over b squared. So we have to be careful with that. We don't want to make the mistake that I did earlier. And you have to pay attention to these very, very carefully because here I might have thought that I met my criteria with that. But what I have instead is I have dx equals du over b. We add 1 over b here, so du over b is dx, and that gives us a b squared out there. So this is the correct answer for the problem as it was written. So we have to be a little bit careful about these things. In fact, I'm going to have to go back in my notes and make some corrections. And these are the types of things that you got to be careful about when you make when you take an exam. So here we go. Let's take a look at another one. We have another problem. We're given x plus 1. And you got to remember that these are all special cases, because there aren't very many cases where an integral can be actually evaluated. I keep saying that, but it is true. So you can beat yourself to death on an integral that can't be integrated, like the bell curve. The bell curve, whoops, I keep giving that as an example, but that's an important example because the bell curve is used so frequently. And that is given by, this is called the Gaussian curve, and that is e to the minus x squared over 2, something like that. And that's the Gaussian curve. It's the bell curve. And you know the famous 3 standard deviations, 3 sigmas gives you 95th percentile, and so on. But you can't take this function and integrate between 2 points, A and B. It's just not, you're just not able to integrate that. And you have to find ways around that, and usually it's in an infinite sum. So we're try and erase this as much as I can quickly. And I keep hitting the shape. My finger's too big here. Alright, so let's just erase this. Clear the board up. I like that example because my brother asked me once to integrate that problem. And I was sitting on a plane, and I was thinking, gee, I can't find a way to integrate this. And so I used a Taylor series. It was a long flight from coast to coast, so I had the time, and I converted the Gaussian curve to a Taylor series, and then integrated that, and then came up with an answer for him. Unfortunately, he wasn't able to follow the procedure very well. He's a PhD forester, and they don't usually delve into the higher areas of math. And so he wasn't able to follow my process very well, but I did get him an answer. I don't know how useful it was to him. So let's see, where were we? Now, we use the substitute again, x plus 1 du whoops, what am I doing? Equals dx. And so we have u to the minus 1/2 du. And now we use our little formula, and we have u to the 1/2 on 1/2 plus c, and then that is 2 u to the 1/2 plus c, and 2 times x plus 1 to the 1/2 plus c. And that is the answer. And that one I did get correct. All right, so I think it's probably time to select projects and mass delete them, because I've got so many here. I don't want to chalk up my board with all these projects I don't want to save. Okay, so let's take a look at another one. Now they're starting to get a little bit more interesting. So we got, remember either the 2x dx. Remember when I said the bell curve e to the negative x squared on 2? Well, this kind of looks like it a little bit, but it's not really that problem at all. So it's simply just e to the x. So we make a substitution, equals u equals 2x, du equals 2 dx, and so we make this e to the u, but we don't have 2 dx, so dx equals du on 2. So we have du on 2, and that's just 1/2 e to the u plus c, and make our substitution again, 1/2 e to the 2x plus c. And that is our answer. And here's another problem of a similar nature, but it's a little bit more complex, and it's something that you need to think about a little bit. So we've got a very interesting one. We got e to the sine x, cosine x dx. And in this case, u equals sine x, and du equals cosine x dx. And that's exactly what we've got in the integrand. So we have e to the u du. And so we're back to that exponential function, which is simply e to the u plus c, and e to the u to the sine x plus c. And that's it. Simple enough. And let's just keep plowing through as we can. They're getting more and more interesting. Here we go. Here's one. Now, these are problems that we have to be careful. There are a lot of problems that look like they may be integrable, but they're not. You have to be very careful about what variables are present and what aren't. E to the x squared dx. Now, remember, this one looks very much like e to the minus x squared that I said was not integrable, the Gaussian curve. But that's not what we got here. It looks similar, but it's not. If we take a u substitution, we've got u equals x squared. We got 2 du equals 2x dx. Well, we got x dx in the integrand, but we don't have 2x dx. So dx is equal to du divided by 2x. And we have du e to the u du and 1/2, because we're missing that 2 there. And the x's cancel. So here we've got 1/2 e to the u plus c. And now we substitute back in 1/2 e to the x squared plus c. And that is the answer. So it pays to pay close attention. Sometimes it's easy to lose your way, like I did on a couple. Now here's one that's very interesting. This one is pretty cool. So let's take a look. We've got anything where we have e to the something, it's worth exploring whether we have an e to the u du situation. And that's what we have here. So if we say that u is tangent x, then du equals secant squared x dx. And we've done this a number of times. I don't have to keep proving that to you. Each time we take the derivative of a tangent function. So now we've got boiled down to e to the u du, and that is equal e to the u plus c, and that is e to the tan x plus c. And that's the answer. It's as simple as that. It looks complicated and it looks intimidating, but basically this kind of clues you in when you see these things that you may have a chance of putting it into this form. This is the key. So let's look at a few more. We've gone through quite a few integrals, actually. It's hard for me to know how to label these videos because we have such a variety of integrations that it's going to be difficult to to advertise which integrals being solved. So if you want a particular integral, it's going to be kind of difficult. You may have to look at an entire video and it may miss. I don't know, maybe I should make a list of videos with what integrals have been solved. So that may be the answer. Okay, 2x dx. And we use u equals 2x and du equals 2 dx. So dx equals du on 2. So we end up with cosine of u du on 2. Now, we have y equals sine x and dy equals cosine x dx, and then y equals cos x dx equals sine x. So we have sine x, or sine u 1/2 plus c, and that is 1/2, and we can draw a box around this, equals 1/2 sine 2x plus c. And there we go. That's correct. Now, we're moving into some additionally interesting. I think all of them are interesting, to tell you the truth. Let's look at this one. This looks pretty interesting. We got x cosine 2x dx. Oh, that's the one we just did. Sorry. We don't want to do that again. Let's see. Okay, here we go. Sine of a plus b dx. Well, now this is, you can, bx. Sorry, let's erase this, make it a little bit more clear. All right, bx dx. And so, you know, it's interesting. We could use the double angle formula for this problem, which would be kind of strange. But here we're going to stick with u equals a plus bx and du equals b dx, and dx equals du on b. So we end up with sine u, and we got du on b, and that is equal to minus cosine minus 1 on b cosine of u plus c, and that is minus 1 on b cosine a plus bx plus c. And that's our answer. But you know what we could do, which is kind of a weird way of doing it, we could say that the integrand sine a plus bx is equal to cos a sine bx plus cos bx sine a. And these would be treated like variables. Constants. These would be like constants, like, oops, I just spastically drew something. Some kind of a constant k, k1, k prime, something like that. Because they don't have the variable in them. And then you would do the integration for these two, and it would be a long way around, but I wonder if you couldn't get the equivalent of this when you apply the double angle formula for the cosine of that of a plus bx. But we're not going to do that. We're going to leave it in as simple a form as possible. It's just an observation that you could do it this way. I wouldn't recommend doing it that way because it's just so much longer adding steps to the process. And so let's keep plodding on. I'm starting to get a little wiped out. Again, I told you we were up very, very late, and I'm about ready to crash again. We didn't get to bed till 4 or 5 o'clock in the morning. So it was a tough night. We had our kitty for at least 7 or 8 years, as she was an abandoned kitty, and our daughter took it in, and then when she couldn't take care of it, we ended up with it, and the poor thing was suffering so badly last night. But anyway, that's part of life. So let's take a look. Let's look at this one. We've got x squared sine of x to the third dx. Well, this isn't too different from what we've done before. We make a substitution. U equals x to the third du equals 3x squared dx. Well, we have the x squared dx, but we don't have the 3. So dx equals 3 du on 3x squared. Or we could just say x squared dx equals du on 3. It's the same thing. So we end up with sine u du on 3. And that's equal to 1/3, and this is cosine of u plus c, and that's equal to 1/3 cosine x to the third plus c. And that should be our answer. And I think I got something mixed up here. So let's say y equals cos x dy equals minus sine x dx. Y equals sine x dx cos x equals. So I left out a minus sign here. It's always good to go back and check. So minus sign equals sine x dx. So that's what we did. We left out our minus sign. So this is the answer right here. Make sure you got that negative sign. And I forget how many we've done, but we've done quite a few. Let's see, cancel. Let's select the projects. 1, 2, 3, 4, 5, 6, 7. Delete them. I hate getting too many problems backlogged. All right, so let's take a look at more. I got 30 of these, and they start getting more complicated. So we looked at that and see if there are any others here that are interesting. I think they're all interesting. Why don't we do one more and we'll call it quits for the time being. So in this problem, we're given secant squared to the 5x dx. So this one, it may help us to say y equals tangent x dy equals secant squared x dx. And so tangent x equals secant squared x dx. And so we'll just keep that as a side note. And we do a substitute. We go u equals 5x and du equals 5 dx. And we have secant squared u and du dx is equal to du on 5. So we got du on 5. And we know what the integral of the secant squared is, so we have 1/5 1/5 tangent u plus c, and then we put u back in, 1/5 tangent 5x plus c. And that's our answer. And we've gone through quite a few integrals. I forget how many. I guess we did at least 10 or 11 integrals, and they were all variants on the basic integrals that we learned in the very first video. We're just basically putting these into a known form. We had the e to the x type dx. We had 1 over x dx type. We had the trigonometric functions. We had the polynomials. And we had all different types, but they were all variants on the same thing. We had secant squared x dx. We had all of these that we had worked out in the first video, but variants on a basic theme. And that's what we did with our substitutes, our substitutions, simplified the problems to a basic form. And that's it. So this is a very, very weary math man wishing you the very best, and so long until the next video, which will come soon, because I'd like to get through as many of these as possible. So with that, I bid you farewell.